Yeah. Okay. Yeah. Yesterday that was too big. Big audience. Mm. Yeah. Yes, that's so perfect. Like, mm. Yeah. Great. Shall we stop? Okay. Maybe there is the future. switch. Oh, and the battery is low. Oh. Maybe can I use maybe the handphone? But the battery is low. Where's the connector to recharge?
I think it's better. I'm going to introduce you and then I will give it to you, okay? Great. Okay. It's true. It's true. But I think it's better for him to move. Okay, so good morning, everyone. I think we should probably start already. Welcome to the second day of the conference. We have two plenaries before the coffee break. The first one will be given by Kiyotomo Ichiki from Nagoya, Japan, and he will be talking about the CMB. In particular, he's going to give us an overview of the current status of the field, as well as some future prospects. You have 45 minutes in total, including questions. So please go ahead.
Oh, yes, thank you. Okay, so good morning, everyone. Thank you for coming this early morning for the early universe physics. I'm Kiyotomo Ichiki from Nagoya University. Today, I would like to talk about CMB, the current status, and future prospects. So this is the outline of the talk today. I would like to introduce a brief history of the CMB spectrum observation in 30 years. And then I discuss the CMB polarization and ranging and the foregrounds in particular, and future CMB cosmology with secondary CMB, with promoting our recent works. Okay, so to warm up, let me start with what is a CMB. So CM is thermal relic photons from the Big Bang in the early universe with a black body spectrum with temperature about 3 Kelvin. And this figure is taken from the COVID virus data in 1996, showing the CMB black body spectrum. And surprisingly, the figure caption said that the error bars are smaller than the thickness of the line. So the spectrum is more than perfect black body. And CMB, so the cosmic microwave background, is very isotropic. But in fact, they have small anisotropies. After removing the monopole and dipole due to our relative motion to the CMB frame, you will see the temperature anisotropy about 30 microkelvins like this. And if you look closer, then you will find that the CMB is linearly polarized with amplitude about microkelvin, as shown in this figure. So these temperature and polarization fluctuations can be generated from two kinds of perturbations, namely the density acoustic waves or scalar mode, as shown in the top panels, and the gravitational waves or tensor mode, as shown in the bottom panels. Important fact here is that in the case of density fluctuations, the polarization direction can be either only parallel or perpendicular to the wave vector of the Fourier mode, K. So this is called the E mode, which is parity even. The gravitational waves, on the other hand, can generate parity odd polarization pattern called the B mode. Wait. Called the B mode. Okay. So this is a polarization image generated by stacking polarization pattern around the hotspot of temperature anisotropy observed by Planck on the left and lambda CDM prediction on the right. And from the figure, clearly you can see that the observed temperature and polarization anisotropies by Planck are dominated by the acoustic density fluctuations and not gravitational waves because the polarization pattern is parity even. So this is E mode. Okay, so here is the history of CMB spectral measurements. Here we show the CMB angular power spectra of temperature, and E mode polarization, and B mode from lensing, and B mode from inflation and gravitational waves. And the first detection was made by a Kobe satellite, which measured TT power spectrum on largest angular scales here. This is in 1993. I was a junior high school student. And in 1999, a Boomerang and Maxima experiment reported the first detection of acoustic peaks, and followed by QMask and CBI and the other experiments. And in 2003, WMAP came in and giving us a beautiful temperature power spectrum from a single experiment. Right? And in 2005, a Boomerang and DESI experiments reported the first detection of E mode power spectrum here, and followed by the other CMB experiments. And by 2013, WMAP has detected E mode polarization power spectrum on the largest angular scales. And in 2015, Planck came in, and it gave us the almost cosmic variant limited TT power spectrum. And the first measurement of the lensing B mode power spectrum was done by SPT Paul and Polar Bear here. And as you may remember, there was a big debate as BICEP 2 reported excess of the B mode power at intermediate scales, which might indicate the evidence of inflationary gravitational waves. However, it turned out that it was due to the foreground contamination, as shown BICEP-Keck-Planck collaboration. Okay, now the Atacama Cosmology Telescope and the South Pole telescopes give us precise measurement, temperature, and E mode power spectra on small scales. And while the Planck give us an E mode measurement on largest scales. Okay, so this is the current status. And in addition to these standard spectra, recently there has been a claim for a possible detection of non-zero EB power spectrum. In the standard cosmology, the EB power spectrum should be 0, assuming the universe is parity symmetric. And interestingly, you may notice that the shape of the EB power spectrum followed the shape of the EE power spectrum, which can be realized by the cosmic birefringence effect. And the statistical significance is around 3 sigmas. And now the BICEP, the Keck collaboration is performing a dedicated analysis of the cosmic birefringence effect. So let's stay tuned. So this is the current situation. CMB experimentalists have improved sensitivity by almost 7 orders of magnitude in the power spectrum in almost 30 years. Now, we want to improve another 2 orders of magnitude to detect the B mode from gravitational waves in the next 10 years. Okay. So historically, the representative CM satellite experiments have been done once in every 10 years. So 1990s Kobe, 2000s WMAP, and 2010s Planck. And here we are now expecting the LiteBIRD experiment, and we strongly hope that it will be launched before 2030 to follow this history. Okay, So this is the latest specification of the LiteBIRD from the recent PTEP 2023 paper. The LiteBIRD has 3 telescopes in a single satellite and 15 frequency bands to mitigate foreground and to detect the tensor to scalar ratio at the level of 10 to minus 3. And all the detectors combined, the noise level can reach as small as 2.2 μK arc minute with the angular resolution up to 18 arc minutes. So this is the LiteBIRD. And the main science objective of the LiteBIRD experiment is to detect gravitational waves from inflations through B-mode polarization on large angular scales. Because LiteBIRD is a satellite experiment, and therefore we have some advantages. So from space, we can access the largest angular scales, and we can escape from the atmospheric emissions, and we can observe at any frequency you want. So here, I show some example of B-mode power spectrum from gravitational waves generated during inflation. And as you can see from the figure, the detecting both peaks at the reionization peak. Who is talking? And the recombination peak at the intermediate L is important to distinguish the different models of inflation. So the LiteBIRD will play an essential role to discriminate the models of inflation. Okay. So however, there is one issue in detecting B-mode signal from inflation. Here, once again, we plot the power spectra, and the target B-mode power spectrum is plotted in red curve. If you plot the sensitivity curve in this figure, the LiteBIRD noise should look like this. And you may think that we may detect the signal. However, there exists notorious foreground emission from our own galaxy, the Milky Way, and the amplitude of the foreground is something like this. So we should deal with this foreground or somehow subtract the foreground to see the gravitational waves from inflation. Okay, so this figure shows what kind of physical processes create the foreground for the CMB. At low frequency range, synchrotron emission dominates, which is an emission from the high energy cosmic electrons coupled to the magnetic field of our own galaxy. And at higher frequency range, thermal dust dominates, which is an emission from the dust grains heated up by the starlights. And in the middle of the frequency, there might be anomalous microwave emission. And for that, let's see the Key Forte talk on Friday parallel session. Okay, so after Planck, there was a CMB survey at low frequency by Parkes telescope called ESPAS. And important message from the ESPAS experiment survey is that it is a quotation. So there is no region of the sky nor frequency where the foreground amplitude right below a CMB B-mode signal is tensor to scalar ratio 10 to minus 3. So foreground removal is essential. So accordingly, in the CMB community, many foreground removal or component separation methods have been developed. This is just a list, not far from complete. And I don't want to explain each of them. But again, here is a quotation from a paper by Joe Dunkley. And she said, as a community, we have a set of tools ready for performing component separation and estimating the CMB signal from observed sky maps. So I agree with her opinion, and we are waiting for the data. Okay. So now please allow me to promote one of our recent work, a foreground removal method called delta map. This method is based on a simple internal template method developed by Katayama and Komatsu 2011. And we improved the method to mitigate 3 issues. The first is the varying spectral parameters in the sky. So we accounted for this issue by Taylor expansion of the spectral parameters, like the moment expansion method. And the second is the decorrelation effect. That is the effect caused by the multiple dust grains with different temperatures and different polarization angles along the line of sight. We can mitigate this by assigning the different dust temperatures for Q and U Stokes parameters separately. And the third issue was the AME component. And we can show, we showed that the AME component can be absorbed through introducing running synchrotron spectral index. Okay, so that's good. So the appealing point of our method is that the method is simple and completely internal. And we have only 6 parameters in the method. So this is very simple. And we have, we show that if we assume the noiseless experiment, then there's almost no bias in the tensor to scalar ratio R. The weak point is that our method is only applicable to the largest angular scales. So if we assume the LiteBIRD noise level, then the method is not so sensitive compared with the other foreground removal method. Okay. So recently, yet another foreground component is discussed in Nashimoto et al. This is so-called CMB shadow. So I'd like to discuss a bit. This arises because non-spherical dust grains induce Q and U dependent absorption of CMB monopole to lead new polarization. So this is the CMB shadow. And we showed that the CMB shadow brings new systematic bias as large as 4 times 10 to minus 3 in terms of tensor to scalar ratio R. So, but the good news is that if we apply the delta map, accounting for this CMB shadow as a new foreground component, then we can mitigate the bias. But anyway, in a future polarization experiment, you need to be aware of this new type of CMB foreground. So even if no gravitational waves were detected, unfortunately, the LiteBIRD guarantees cosmic variance limited E mode measurement on large angular scales, which enable us to determine the optical depths at this the cosmic variance limited level. And this is very important in the future to constrain neutrino mass. And not only the total optical depths, but E mode, the precise measurement of the E mode power spectrum shape will give us a chance to discriminate the physical reionization models as shown in our paper. Okay, so now let's move on to the different topic. So this is CMB ranging. Because CMB ranging is rapidly developing tool in observational cosmology, so I would like to mention here a bit. The CMB ranging is a gravitational ranging effect due to the large scale structure of the universe. And the effect, surprisingly, the effect was already discussed in 1987 by these authors. And even when the fluctuations of the CMB themselves had not been detected yet. So I appreciate their big, theoretical imagination. So here we show a schematic picture of the CMB ranging. And here, I would like to tell you 2 important angles. One is the deflection angle alpha, which is given by a deflection angle per per unit scattering times a square root of the number of scattering, which gives you the angle 2 arc minutes, which you might think small. However, the deflection should be coherent over 2-degree scale. This is because the large scale structure of the universe is also coherent over that scale. So because the 2-degree is the acoustic oscillation scale in the CMB power spectrum, so this is very important effect. So a bit history about the CMB ranging. So the effect was first detected in 2007 through a cross correlation between the CMB map from WMAP and the large scale structure map from the SDSS. And 2008, it was also indirectly detected through the smoothing effect on the TT angular power spectrum by the Akbar experiment. And the direct estimation of the ranging power spectrum became possible only 10 years ago, about 10 years ago. The first detection was reported by ACT experiment, followed by SPT and Planck satellite. So the CMB ranging complements the information from the primary CMB anisotropy because the ranging provides information about the distance to the intermediate redshift and matter, so the amount of matter, amount of gravitating matter, and its amplitude fluctuation, sigma 8, at that intermediate scale. So using these informations, we can break the degeneracy in distance to the last scattering surface, so-called omega k H0 degeneracy. And also we can break the degeneracy between tau, the optical depth, and the AS. This is the amplitude of primordial density fluctuations. And breaking this degeneracy is important again to constrain neutrino masses. Okay. So a month or 2 months ago, the ACT and SPT teams published their latest result on the CMB ranging. So this is the progress in 10 years. So the left panel shows the CMB ranging power spectrum from ACT, and right panel shows the ranging power spectrum from SPT. And the curve, so black curves are the model prediction from Planck, so the lambda CDM model. So the data looks completely compatible with the theoretical prediction. And the cosmological parameter constraints look like this. And so let's start the neutrino mass. So the neutrino mass has been already severely constrained at the level of 0.12 electron volts. So this is almost the mass scale of the inverted hierarchy model. And regarding the curvature of the universe is okay with flat. So the omega k is consistent to be 0. And as for the interesting parameters now, so the H node and sigma 8, it seems that the ACT and SPT are completely on the side of the Planck. So for this tension problem, let's look forward to the talk by Eleonora, plenary talk on Friday. Okay. So finally, let's discuss future directions. It seems there are 3 ways to go. And the first one is, as we discussed earlier, E and B mode polarization on largest angular scales, mainly by the CMB satellite or balloon experiments. So the main science objectives are the detecting gravitational waves from inflation and cosmic reionization history and neutrino masses. And the second way to go is go a relatively smaller angular scales with larger aperture, so the larger telescope on the ground. And using a CMB here, using the CMB as backlight, we can map out our universe, both for dark matter and baryon through CMB lensing effect and a number of near F0 bit effects. And the third way to go is the spectral distortions. And by measuring the spectral distortion away from the perfect black body spectrum, we can estimate the energy input in the early universe before recombination. And the estimate can be used to, let's say, probe the acoustic wave dissipation or particle decay energy input and so on. And using the spectral distortion, we can probe the PK, so the power spectrum of initial density fluctuations up to the very small scales, the wave number as large as 10 to the 4 megaparsec inverse. And so this offers a unique opportunity to probe the primordial fluctuation in such small scales. So from now on, let's discuss a bit about the second way to go. So the small angular scale CMB observations. So my favorite future CMB direction is the 3D velocity reconstruction using the kinetic Sinief-Zelbich effect and the moving lens effect. So the KSG effect, the kinetic Sinief-Zelbich effect, as shown in the top left panel here, is the Doppler effect on the CMB photons scattered off by free electrons along the line of sight, and can therefore probe the radial velocity of the density field. And the moving lens effect, on the other hand, is nonlinear integrated Sachs-Wolfe effect, as shown in the bottom left panel. And using this effect, we can probe the tangential velocity of the moving clusters. So these are very complementary. And combining these with large-scale structure data, we may reconstruct 3D structure of velocity field, which in turn can be used to probe the growth of structures, and therefore we can use them to probe the nature of dark energy and modified gravity and neutrino masses. Okay, another my favorite future CMB observation is using a free electron in clusters of galaxies as mirrors at distant universe, scattering CMB photons. Scattering induced linear polarization, so shown nice animation by Wenfu here. So this is called the polarized Sinief-Zelbich effect. So the polarization can be primarily induced by the CMB quadrupole seen by the free electron. So this polarized SG effect can probe the remote CMB quadrupole seen by the cluster. So it can be used to probe the large-scale fluctuations of the universe, and can be used to estimate optical depths beyond the cosmic variance and the cosmic birefringence and gravitational waves, and also the integrated Sachs-Wolfe effect due to dark energy. So another SZ effect, and I think this is a less known name, called the BSZ effect. This is Blue-ring SZ effect, and will be also interesting in far future, where it can directly probe CMB temperature towards cluster direction. So this can be used to isolate the Sachs-Wolfe contribution and integrate Sachs-Wolfe contribution. Thank you. So using a couple of minutes, here let me promote our recent work where we used polarized CFZ effect as a probe of dark energy. So this is a paper, and this is a collaboration with Sumiya Kun, this is a graduate student, and Guo-Chin Liu. So the idea of this method is very simple. We assume a number of galaxy clusters from which we measure the polarized CFZ effect. And using this information from the polarized CFZ effect, we may reconstruct a density fluctuation on very large scale, so the largest scale, from which we can predict CMB anisotropy that should be observed by us from the solar system. So this is a prediction. So we can directly compare the prediction from the cluster of galaxies and the direct measurement of the CMB anisotropy viewed from us. We can infer the dark energy models, because the important point is here that predictions is done by using cluster polarizations where the dark energy effect was not significant because the position of the clusters are far distant in the universe. And therefore, the difference between the prediction and the observation can be used to detect the integrated Zaxborn effect. So this is a constraint on the dark energy equation state parameter W that was introduced already by the plenary talk yesterday. So this is the ratio of the pressure of the dark energy, the ratio, the pressure, and the energy density. And the result depends on the assumed noise level. But in the ideal noiseless limit, the 1% determination of the dark energy equation of state W is possible only from the CMB information. So this is possible because in this method, we effectively measure the cosmological density field twice, and therefore we do not suffer from cosmic variance. So the final one is the blue-waring SZ effect. So this is a very idealistic and futuristic idea, but it is very important. If you look at the the CMB textbook and the transfer equation, you can find that the CMB temperature anisotropy after the recombination is given by this. And the most significant contribution is coming from the KSZ effect. So this is a Doppler effect. But there was another effect called the BSZ effect. And the relative amplitude is something like this. So if you can assume that once you can remove the thermal CFZ and the kinetic CFZ effect can be removed out, then you can find the CMB map, something like this. And this is basically the Zaxborn fluctuation. And you can see that some clusters here and some blue-waring effect due to this term. So the simple formula here, that the temperature fluctuation by the blue-waring SZ is just the optical depth of the cluster times the intrinsic Zaxborn temperature fluctuation. So if you can use this, then you can use this effect to infer the original Zaxborn effect seen by the cluster towards the cluster direction. So the BSZ is negative if background Zaxborn is positive, and BSZ is positive if the background Zaxborn effect is negative. So this is the BSZ effect. So using this, in the far future, you can use this BSZ effect to separate the Zaxborn contribution and the integrated Zaxborn contribution. And once you can do that, then you can cross-correlate the integrated Zaxborn map directly to the large-scale structure data. And thank you. And in this case, you can analyze the integral Dax-Wolf effect without the cosmic variance from the Dax-Wolf realization. So this is the summary. So CMB anisotropy observations are steadily evolving from the 1990s. And the sensitivity, the CMB experimentalists have improved by 7 order of magnitude in 30 years. And we discuss foregrounds may be a big issue, but the community is ready to address it. And we will see first evidence of gravitational waves, hopefully, in coming less than 10 years. So the 3 future directions, we discussed 3 future directions. So polarization, observation on large scales, and small scales, and the spectral distortion. And we discussed that using CMB as a backlight, reconstruction of the large scale density fields and the velocity field of large scale structure will be possible, which will enable us to probe the cosmology even beyond the cosmic variance. So I stop it. Thank you very much.
Thank you so much for the great overview. So there's
a brief one. We were talking about foregrounds. 10 years ago, I remember there was a lot of discussion about the spinning dust, but you didn't mention it here. What happened?
So spinning dust is still a matter of debate. And I think that especially the key hope the experiment in here is the spinning dust is one of the main targets of the observation. And they place an I think upper bound on the polarization degree, and that is about less than percentage. So it's not so big, but in the future maybe we should take account for.
What about the frequency band? Do they cover many frequency bands? We can just dependence of the dust to remove it?
Yeah, the spinning dust is typically in the range between the synchrotron emission and the thermal emission. So that's between in between. So I brought the by the from the
oh, more time, more questions, sorry.
So you mentioned that conclusion, we will see the inflationary gravitational wave in the coming 10 years. So what if we don't see something like is there some other proposal such that we can say for even small, is there some proposal?
Yeah, there's some futuristic TMB experiment proposal, but as far as I know, no project funded, not funded yet. And yeah, I think you can refer to the name of the CMB, HD, or DESI project for the future, future series experiment.
Okay. Before the mic, guys. Paulo.
Yes, so you went through the various techniques to remove the contaminations, but at the end of the day, once the map is clean, and so what would be the key point that allows you to say these B modes and not some additional unknown spinning, rotating, oscillating dust?
Yeah, that is a good question. And so the most, let's say, important thing we should check is the inflation, let's say, generated gravitational wave to be close to that. So the resultant any component
We still have more time for questions, if any. Nagisa?
Thank you. So related to topics with this slide or the few slide after this dot. So I'd like to ask about the CME shadow. So naively, I guess that statistically with some over the line of sight, the effect can be cancelled. Why the effects can remain in such a large value after the integration?
To cancel, I think you have to assume that the many dust is coming.
Yes.
But
But if we collect many line of sight, still but it only consider line. I see. Thank you very much.
Any more questions?
Hello, maybe this is kind of a little bit off topic, but I've seen that in the last years there have been some articles kind of claiming that we are maybe taking the Doppler shift, like calculating it wrong, calling it the Hubble flow, and basically from taking that small, changing that small thing inside the CMB analysis, they can get to a universe that basically has no cosmological constant. Would you say that there is like even a small chance for that to be true?
I don't think I can answer your question right now. So
Okay, thank you. Yeah.
you discuss later.
Okay. We still have some time for questions. At least maybe one more, if any. Okay, so if not, let's please thank the speaker again.
Thank you very much.
Yes. Yeah, it works.
You show me 5 minutes? Yes, okay, you then, okay, sounds good, sounds good. Okay, sounds good. It's not the first talk. But that is not. We do it, it's not the first slide. How do you measure? It's frozen. No. Okay. Yeah, but you're going, how do you go to back here? Okay, thanks. Sorry.
Can you hear me? Yes. Next talk, yes. Next talk will be by Paolo. Next talk, now yes, will be by Paolo Creminelli. He will be talking about inflation. Thank you. In particular, he's going to focus on perturbation theory and also beyond perturbation theory. So, Paolo, you have this 45 minutes total, including questions.
Okay. Thank you very much. So first of all, let me thank Juan for the invitation. It's really great to be here, and I'm looking forward to learn from all of you during this week. I'm going to talk about inflation and non-gaussianities, and after an introduction, I will also motivate to go beyond perturbation theory, and of course also the talk tomorrow of Enrico Payer will cover different directions, but of this topic. I cannot go to the second slide. Okay. So the question, we all know that a very important question in cosmology is whether the primordial fluctuations are Gaussian, that is to say described by just a two-point function, or there is evidence of something that goes beyond that, most notably the bispectrum, so the three-point function. So we're asking whether there are interactions in the original perturbations. I'm sorry, but I don't know the direction. And the experimentalists are great, and we have very, very tight bound on non-gaussianities. So this is the bispectrum, and usually we parameterize the amplitude of the bispectrum. We select a shape of the bispectrum, so I chose the two of them, and we put bounds on the possible amplitude of the bispectrum. And you see the bounds on FNL local and FNL equilateral are really great. And remember that these numbers must be multiplied by the RMS fluctuations, which are of order 5, 10 to minus 5. So we are saying that we know that the universe is Gaussian with corrections of order 10 to minus 3, 10 to minus 4. So it's just amazing as an experimental result. I remind you that equilateral non-gaussianities basically mean that there is a correlation among modes with similar wavelengths, while the local one has correlations among modes of quite different wavelengths like this. So we're still far from what the very minimal model of inflation predicts. This was calculated by Maldassina more than 20 years ago. And this number is very small. It's of order slow roll, it's of order 10 to minus 2, so it's very, very far in the future. And the effect comes from gravity. So so it is the Witten diagram. So it's small also because it comes from gravity. Now, why it's so small, I remind you, is small because our basic model of inflation is based on slow roll. And slow roll means that the potential is flat. And therefore, it says that the interactions which are coming from derivatives of the potential are very small. And in order to quantify this, let me remind you that if I look at the quartic coupling of the inflaton, I look at the quartic coupling because it's dimensionless. it's constrained by slow roll, by the same logic that it leads to the first two slow roll parameters. So if you require slow roll to continue for many e-folds, you get a bound which is much smaller than 10 to minus 10, is over the 10 to minus 13 or smaller. So we know that if you have slow roll means that the quartic coupling on the inflaton is small. And I want to compare with the Higgs, which has a quartic coupling which is over the unity. Okay, so that's why in the minimal model of inflation, non-gaussianities are very small and actually are dominated by gravity. So in the last 20 years, many people in this room, so I didn't put citations because there are too many. So in the last 20 years, what emerged is that, I mean, the bottom line is that whatever you do with inflation, starting from the very simple minimal model, you enhance non-gaussianities. Let me give some examples. So you can have the derivative interactions. I said that potential interactions are suppressed by slow roll, but derivative interactions are allowed, and they can be big. You can go to multi-field, looking at the curvaton or variable decay scenarios, so going beyond the single field scenario. You can look at warm inflation in the presence of a thermal plasma, which is self-sustained. You can look at other forms of dissipation. You can even look at different forms of inflation with different symmetries, like solid inflation. Or you can look at features in the potential. Or even if you're brave enough, you can look at even at alternatives to inflation. And in all these cases, you enhance non-gaussianities. What I want to stress is that not only you enhance non-gaussianities, but I think it's very important to stress that there is an important goal, which is reaching FNL over the unity, both in the case of local non-gaussianities and equilateral non-gaussianities. And I think it's very important in the sense that this is a theoretical goal, which is very important even if you don't observe things. And this, I think, is very different from when we say about constraining, I don't know, dark energy or strong gravity. In those cases, it's not so easy to have a very definite theoretical goal. But here, I would say that in all these cases, reaching FNL over the unity will basically tell me that effects are not important. Okay, I should enter more into details, but for instance, about derivative interaction, if you reach FNL over the unity, you say that basically CS cannot differ much from unity, cannot be 1/2, for instance. In the case of, say, the curvaton, it's quite difficult to have FNL smaller than unity, and you can add these effects of dissipation or warm inflation must be subdominant. Otherwise, you violate these inequalities. So it's not a theorem, but I think it's a very, very important theoretical threshold. Sorry, and hopefully an experimental threshold that can be reached. Of course, there is a difference between equilateral and local in terms of experimental results, but in both cases, it's important to get there. So I'm not, of course, an experimentalist. So I took one picture, but I could take many. So it's not, I'm not advertising particularly this kind of experiment, but just to show that there is hope for the future. So these are Planck results. So here there is also the orthogonal non-gaussianities, which are similar in spirit with the equilateral one. And you see these are the Planck bounds. This is the forecast for CMB stage 4. And then there are a bunch of experiments, but I could list many, many more. What I want to stress is that if I look at local non-gaussianities, there is a path to below unity, which is kind of robust. More difficult for equilateral non-gaussianities. So this PUMA experiment seems to go to few. Okay, it's not one. I mean, the threshold is not very, very precise. So, well, 2 is not so bad. And we should be excited about this future because, as I said, I think there is a very important theoretical threshold. And even if we don't observe something, we're going to see that all these effects I was talking about are subdominant, and we are very close to the simplest model of inflation without additional features. So from the point of view of theory, we know in all these models how to do calculations. So we learned in the last 20 years. And it's all based on perturbation theory, in particular on in perturbation theory. So imagine that you have a quantity that you want to calculate, and you take the free approximation, and then you dress it with evolution operators. So the only difference compared to the standard S-matrix calculation is that in the universe, we only know the vacuum in the past, not in the future. And that's why it's called in. So you have to go back in time to project in the vacuum. So you see that here there is an anti-time order operators, which does not appear when you do the S-matrix calculations. And let me stress that in order to project on the vacuum, I need to do a small Euclidean rotation to project in the interacting vacuum. So let me do an example. So just an estimate, just to see. So imagine that I have the free action for zeta. This is the canonically normalized zeta, and I put an interaction. For instance, the time derivative of zeta fourth, and of course, everything is of order Hubble during inflation. So both the scale of zeta, of the canonically normalized zeta, also derivatives. So if I suppress this operator by h to the fourth, the signal that I should see is of order lambda. So lambda is the parameter that tells me that perturbation theory is working. And in particular, I will see a trispectrum in this case, because it's a quartic interaction, which is, so this ratio, which is the non-gaussianity, is suppressed by lambda. And experimentally, we know that this is small, and that's why perturbation theory works well. And the same thing with the work for the bispectrum. So everything is good. So now you can ask why in the title I put to go beyond the perturbation theory. So since the perturbation theory looks great here, because both experimentally and theoretically we should be able to use perturbation theory. So let me motivate why it's nice to study also what happens on perturbation theory. So if I look at the probability distribution of zeta, let me focus on a single variable. Of course, there all is momentum dependent, so there are many momenta here, but let me focus on a single variable. So there is the Gaussian part, and then there are corrections which give the bispectrum and the trispectrum, which are cubic and quartic in zeta. So if you factor out the Gaussian part, you see this. So the correction to unity is given by this ratio or this ratio, okay, which are these quantities. What I want to stress is that the parameter that tells me whether perturbation theory works or not is it depends on zeta. Okay, so if zeta is replaced by the typical fluctuation, I get back to what I was saying before. But if zeta is large, then standard perturbation theory is not applicable. So what I'm saying is just that when I look at the distribution, if I look at the modification of the distribution for typical values, I can use this kind of expansion. But when I look at the tail, well, this does not work. Okay, so this is not standard perturbation theory does not tell me anything about the tails of the distribution. Another motivation, which I hope I have time at the end, is that in some models, this expansion does not make much sense. Actually, there are models in which the bispectrum, the trispectrum are negligible, and all interactions are only in endpoint functions at large n. Okay? So this is somewhat, it's also somewhat related to what Gonzalo will talk about, but it's on a different context. So on the tail, the usual perturbation theory does not work. So you can say, okay, but why you are interested in the tails? At the end, the tails are unlikely. That is true. On the other hand, so I give you my motivation. So first of all, it's the wave function of the universe. Okay, so it's not the wave function of some crappy material in my lab. Is the wave function of the universe. Is our mother. Okay, mother is important for Italians. And no, I mean, I think that we must be able to know the answer even in principle. Okay, so I want to know this object as much as I can. Okay, let me stress, sorry, before going on, that this has nothing to do with stochastic inflation. Okay, so we know how to resum non-gaussianities evolving outside the horizon. This is something that we have to do. So, but this is something different. So I'm talking about horizon crossing. Okay. So effects which cannot be approached using stochastic inflation. Okay, another motivation is that black hole formation, of course, is sensitive to zeta of order unity. The expansion parameter I was talking about is FNL times zeta. And we don't know whether FNL is much smaller than unity. So experimentally, we don't know. And also, if you have a small breaking of slow roll, FNL tends to become over the unity. So this is not obvious that you can use the usual perturbation theory. This kind of questions is also relevant for eternal inflation for all cases in which your it is in the full PDF, not only the typical fluctuation. You want to know how likely it is to fluctuate maybe in another vacuum or very far away from the typical trajectory. And as I said, there are also cases in which the signal can be there, but it's not in the bispectrum, trispectrum, and so on. It's in some very large n correlation function. Okay, so these are cases which may be approached using the method that I will tell you. Okay, so the main idea is that in order to study fluctuations which are not typical, which are on the tail of the distribution, well, if they are non-typical, it means that they are large compared to h bar, because h bar is what sets quantum fluctuations. So this means that being non-typical is the same as having small h bar, which is the typical expansion for semi-classical calculations. Okay, so the bottom line of the talk is that in order to go to the tail, instead of using the standard perturbation theory, I have to use a semi-classical calculation. These are a couple of references. So some is quite old, but there is some work in progress, probably more than one paper coming out with some people also in the audience. So my idea is to explain the logic in the simple case of an harmonic oscillator, and then the rest, I mean, it's much more complicated, but the logic is the same. So imagine that you go back to university and you study the quantum harmonic oscillator, and they tell you to do perturbation theory. They tell you add a quartic interaction with a parameter lambda. So this is the typical fluctuation, so the typical size of the wave function. Imagine that you are in the vacuum, and they tell you calculate the correction to the ground state energy of order lambda, lambda square, lambda cube, and you do it. And this is what we do in inflation. We do perturbation theory lambda. But now there is a more complicated exercise, which is I want to study the tail, so the behavior of the wave function for large x. So of course, when x is large, this becomes of the same order as this. So I cannot use perturbation theory. So the parameter now is x bar, which is lambda x over d squared. So which is the comparison between these and these. So let's assume that I'm in the vacuum, like in the case of inflation. So what do I do? Well, I use semi-classical methods. I can use WKB, or I can use the Euclidean path integral, which is close to what I will do in inflation. So let me remind you very briefly. So this is the Euclidean evolution between an initial position xi and the final position xf. It can be decomposed in eigenstate of the energy, and going to Euclidean time, for large times, you are dominated by the ground state. So for large time, this sum is basically reduces to the ground state. And I want to study the ground state as a function of xf. This is the wave function. Let me put xi equal to 0. This can also be written in terms of a Feynman integral in Euclidean, which is the integral over all trajectories weighted by the Euclidean action. And in semi-classical physics, so in the limit h bar going to 0, this is dominated by a trajectory, a classical Euclidean trajectory, which is the dominant. So I solve this integral in saddle. I find a trajectory which is dominant, and then there are corrections which are suppressed, which are the fluctuations in around this trajectory. Okay, so let me skip the details. So this is the solution, the Euclidean solution. So being Euclidean, you have to flip the potential, you remember, and you find a solution which goes from xi to xf. So this is the solution that you have to plug in. You take it, you put it in the action, and you calculate the wave function. Okay, you see now this wave function can be trusted also when X bar becomes large. Okay, so if you go to the tail, this is trustworthy up to corrections of order lambda. Okay, so it's another way to do it is using the WKB approximation, but this cannot be generalized to quantum field theory, but you get the same result. So it's a semi-classical approximation. Now I can do the same for inflation. So I remind you that let's start with a Gaussian case. So the usual calculation can be recast using a functional integral. So the wave function as a function of zeta. So zeta 0 is the late time configuration, and this is the wave function that tells me how likely these configurations are. Is a functional integral starting from the vacuum to the final configuration, and you have an integral over zeta of the action. So for a Gaussian case, the full solution is the same as the semi-classical solution. So in this case, the solutions are the usual mode, the usual evolution that we're used to, that they have a certain value at late times. So you take these, you plug it in the action, you calculate this exponent, and you get this result. And you see that apart from a phase, you get the usual scale invariant power spectrum. Okay, so this is e to the this is the probability distribution. So it's a Gaussian with a variance h squared over k cubed, which is the usual scale invariant power spectrum. Now, so this is the Gaussian case, and usually what we do in cosmology, we use perturbation theory. So these are usually called Witten diagrams, which are the perturbative corrections to what I was saying before. So if you have an interaction which is quartic, I have graphs of this form, and then I have loops like this, and so on and so forth at higher order in lambda. So what you can convince yourself is that since I'm interested in the tail of the distribution, these diagrams are dominant, diagrams without loops. And this is the same as I was telling you before. You are dominated by semi-classical physics, that is to say, nonlinear classical solution in Euclidean time. Okay. So basically, what a semi-classical calculation does is to resum all these diagrams, disregarding all the loop corrections. So this is what you should do. So this is these late times, these early times. So imagine that you are interested in the wave function for a given configuration. So you fix this configuration at late times. At early times, you are in Bunch-Davis. So you decay exponentially if you are in Euclidean space. So this fixes the vacuum. In the middle, you have a nonlinear solution that you have to find. Once you find this solution, you plug it in the action, and this gives you the wave function. Okay. So let me apply this to a couple of examples. So this is the general logic. Of course, it's complicated in the sense that you still have to find a solution to a nonlinear partial differential equation. Okay, so because you need this solution to plug it in the action. For instance, we studied a couple of examples. So one example is you choose an interaction, the interaction I was talking about at the beginning, which is zeta prime to the fourth, so a quartic interaction. Is a particular limit of the effective theory of inflation, but it doesn't matter, it's just an example. So the action now is the free action plus a quartic interaction. So the equations of motion are nonlinear, and in Euclidean time, they take this form. So it's a partial differential equation with nonlinearities. So it's particularly difficult to solve. So you cannot solve it analytically, but you can approach the problem using some analytical approximation and some numerical calculations. And at the end of the day, in this example, we were able to prove that the wave function on the tail, so for very large values of zetas, instead of going like Gaussian, it goes as zeta to the 3/2. Okay, and these are the solutions that so for small nonlinearities, you have the usual, so this time, and this is R. So we look at a particular spherically symmetric configuration, this is the usual Gaussian result, while turning on interactions changes the solution and gives this kind of behavior for the wave function. So the last example that I want to mention is the case of resonant non-gaussianities. So this is something that has been studying a lot in the past. These are a couple of references, but I should add more. So it's the case in which on top of the potential, a slow roll potential, you put oscillations, which are small. So they are tiny oscillations, and they are so the smallness of the perturbations is this parameter B tilde, which tells me that they give a small correction to the Hubble parameter. And usually one is in a regime in which they are frequent, in the sense there are many oscillations per Hubble time, which is parameterized by this alpha. Alpha is large and beta tilde is small. So the reason why this is particularly interesting is that, well, first of all, I have another parameter to play with. So I can study the wave function of the universe for small beta tilde, but completely nonlinear in zeta. Okay? So, but I can expand in this. Another reason why this is interesting is that you see, since these features are of short wavelengths, of course, the expansion of using bispectrum, trispectrum, and so on breaks down very quickly, because, of course, I cannot describe, if I expand around a given point, I cannot describe a jump, for instance, to the other minimum, okay? So you can convince yourself that the expansion now is alpha square zeta. That is to say that when alpha square zeta becomes larger than unity, you cannot use the usual perturbation theory. Okay? Instead of being zeta, is alpha square zeta. So it's very close to what to the typical fluctuation. And then I cannot comment on this, but it turns out that the loops in this case are always negligible, also for typical fluctuations, not only on the tail. So it's another simplification. Okay, so I just want to flash this complicated formula. I just want to state it's quite explicit. So this is the wave function of the universe. This is the Gaussian part, and this is the correction at first order in B tilde. Sorry, I didn't say this. So the simplification is that at first order in B tilde, I don't need to solve a complicated PDE. I just have the solution for beta tilde equal to 0, so the usual Gaussian solution, and I take this solution, I plug it in the action. So I don't need to solve any PDE. That's why I can be explicit about the wave function. So if I'm interested in a given configuration zeta bar, I put this zeta bar here. I calculate the Gaussian solution in Euclidean time. I put it in the action. So this is the action. Forget about the second line. So this is the action. So this zeta is written here, and this zeta is written here. So I'm left with calculating this integral, but it's not a functional integral. It's an integral over time and space. So everything is complicated, but it's explicit. So it's a convergent integral. There is no differential equation to solve. You can check that the Euclidean rotation is okay, and it's convergent at early times. And you can also sometimes do these integrals in saddle point. So you can be even more explicit and finding an explicit expression for the wave function of the universe at any order in zeta. So it's not perturbative, it's non-perturbative in zeta. Okay. Yes. So very quickly, these are the results. So this is for positive zeta and for negative zeta. So the first thing is that you see there is no symmetry at all. So there is a complete different behaviors depending on the sign of zeta. And moreover, there is a very unexpected from the point of view of perturbation theory. So there is a new phenomenon, which is only beyond perturbation theory, which is when alpha square zeta becomes larger than unity, you have some growth, which basically approximately goes as e to the alpha. Okay. We are still understanding, but this is just an example that there are phenomena which are completely not within perturbation theory. And this is just to say that, as I said, this kind of calculation can be done in saddle point approximation. This is the position of the saddles. So you can check that you can do the calculation analytically and numerically, and you see that everything is consistent. So actually, I'm going very fast apparently, but so this is the last two slides. So I was commenting before on some strange situation that I think deserve more study, which is the case in which non-gaussianities are not in the bispectrum, trispectrum, or whatever, but they are only in a correlation function at large n. Let me explain what kind of models I have in mind. So it's the same model as before, is resonant non-gaussianities, but in a regime which has not been explored yet. And so if I want to know the typical size of an endpoint function in these models of resonant non-gaussianities, so they go as b tilde, which is the expansion parameter, and then they go as omega over 4 pi f to the n. So omega is the frequency of these oscillations, and 4 pi f is well, what you expect. So it's like in the case of pion, f would be f pion, is the scale that tells me the periodicity of my potential. So naively, if you look at this, you would say, okay, of course, I need omega to be below 4 pi f in order to be inside the effective theory, because 4 pi f usually is the cutoff of my effective theory. So usually this tells you that the signal is in the correction to the spectrum, n equal to 2, or maybe some bispectrum, and then it dies out. But it turns out that there is another regime that has been explored for completely different reasons in the beyond the standard model community in this paper, in which omega is higher than 4 pi f. And the reason is that actually the cutoff is not 4 pi f, but it's higher for very small b tilde. Okay, so if I go to a very, very, very small b tilde case, I can have a regime in which omega is larger than 4 pi f. And in this case, you see the signal. I leave some details to this paper, which is very nice. Basically, you have a model in which interactions are dominated by large endpoint functions. Okay, so there is no low point function, but everything is in the high point function. Okay, so which is this regime over here. So in this case, I still don't know how to think about this. So we are saying that in the CMB map, maybe there are very large non-gaussianities, but there is no bispectrum, no trispectrum, and so we are completely blind to it. But it could be completely non-Gaussian. Okay, so this is something to think about. So I'm already done. So my conclusion are well, first of all, let me remind you that I find this threshold to be extremely theoretically motivated, and the experiments are getting close to. So this is very exciting. And these are some conclusions about the study of the wave function of the universe. I think it's in general important to understand as much as possible of these objects, both for theoretical and phenomenological reasons. So thank you very much.
Thank you so much, Paolo, for the nice and comprehensive talk. So there's plenty of time for questions. Start with one.
Paolo, thanks for your talk. So clearly a large curvature fluctuation immediately brings to our minds primordial black holes. So do we have an idea of not just the amplitude, but actually on what scales, would be the masses of those black holes that you would predict from those effects?
Yes, it's a good question. I have to say that although the original motivation for these studies were also primordial black holes, I didn't, at the end of the day, we're still studying the theory. Let me go back to so for instance, in this model that we studied, it's very, I mean, the answer is very model dependent, but in this model that we are studying, this is a completely scale invariant model. So of course it's not very suitable if you want to generate a primordial black holes. So in this particular case, we just say that the tail of the distribution is modified at horizon crossing by these effects. But then if you want to get closer to primordial black holes, you should put this into a model in which scale invariance is broken, and we didn't do that. But it is something that we should do.
The features you were showing in the other figure actually seem to give you a larger.
Sorry, you're talking about
the other model.
Oh, the other model. Sorry. I'm going the other direction. For some reason, to go forward, you have to press the other button.
The one before.
Yes. No, sorry, maybe I was not very clear. So this feature, notice. So yes, no, let me repeat because I went fast on this. So this is basically the probability or the wave function of the universe as a function of zeta, not as a function of the scale. Okay, so what I'm saying here is that so there is a very enhanced tail of at positive value of zeta when alpha square zeta becomes larger than unity. We are still trying to understand what this means. In a sense, as I said, we are doing this analysis at first order in B tilde. So I don't know. So of course there is a very big enhancement, which is some sort of resonance, but I'm not sure what will cut this off. Yeah, it's still something to be explored. So,
More questions? More comments for Paolo?
Ciao, Paolo.
Yeah.
Thank you for a very nice talk. I actually have a lot of questions, but I'm gonna start from this slide. So in this comparison, what happens at psi equals to 0?
at zeta equal to 0, you mean?
Sorry,
Yes. Well, there is another plot. We didn't. So there is another plot in the draft in which so for small value of zeta, you should go back to the standard perturbation theory. In fact, this is what we checked. So very close to when you join these pictures, you see that there is a regime in which actually you can check is a nice check of your results that the modification of the wave function is also what you can get using perturbation theory. Okay. Yeah, but I didn't show these are just the tails. I'm focusing on the tails.
And concerning your last point, how large is n, so that we can start seeing this?
Good. Yes. So this n is yeah. So let me go here. Which direction I'm going? Yes, here. This is a model dependent, but I can tell you. So in this paper, not only they present this regime for completely different reasons, but they also have a UV completion of this, so you can be inspired by this. So this n in the particular model they are studying is related to the charge of some field which plays the role of the UV completion. So if you have a U1 field, so this n is sort of related to the charge of this field, and you're taking this charge to be large. So, for instance, if you take this charge to be of order 10, then you get a model in which the important correlation functions are of order 10. So I'm not saying that there is one unique. It's a very strange situation in which you have many correlation functions which are large. They go like n plus or minus square root of n. So yeah, it's something that I think we have to think about how to study, because it's not. I'm not saying that there is a unique endpoint function that becomes large. It's more that there is a broad range of endpoint functions centered around a certain value which become large with very small signal in the bispectrum and trispectrum. But this is something really that we don't know. I mean, we know the theory, but we don't know how to look at this, and it's yeah, we can discuss. It's very interesting.
Okay, thank you. There are a couple more questions up there. Indeed, 4 questions up there. I think we have time for all of them.
Hi, thanks for the very interesting talk. I had a question.
Sorry, what are you? Okay, sorry. Yeah, yes.
At a couple of points, you mentioned that with these semi-classical methods, you are able to compute the wave function of zeta at horizon crossing, which is an improvement because you don't need to do any kind of gradient expansion or similar, I guess, right? But is there anything particular about horizon crossing, or can you use this to get a time-dependent wave function that you can evaluate at any time and at some point cross-check with a gradient expansion calculation outside the horizon, far outside the horizon?
Yeah, good. No, there is no reason why. So I was focusing on horizon crossing because here I'm looking at single field models so there is an attractor, so there is no evolution outside the horizon. So that's why I was terminating my discussion there. But of course, if you have a model in which you also have to take into account super horizon evolution or also some stochastic evolution, you can put this together with this. But let me stress that so these are different effects in a sense that so if you want to apply this to the putting these together with the stochastic formulas, what I'm saying here is that the noise here that you have to put it in the stochastic formulas is completely non-Gaussian in the sense that sorry, it's Gaussian for typical fluctuations, but we are discussing about how the noise behaves on the tails. But yeah, of course, you can put this together and also study the super horizon evolution.
Okay, thanks.
Let's take the next question. There are a few. This is great. Thank you.
Thanks. Hi, Paolo. Thanks for the nice talk. In your second example, you showed the action. I was wondering because I was expecting an action where zeta will have only gradients acting on it, but you show that there is something more. There's a cosine with.
Sorry, which case we're talking about? You're talking about this case.
In the
sorry,
yes,
I
exactly.
mentioned two cases. Sorry, maybe I went too fast.
Yeah, that's it. That's it.
I was talking about a case in which the interaction is zeta prime to the fourth, so a derivative interaction, and then I was talking about these restaurant non-gaussianities.
Exactly. No, I'm happy with this example. But then my confusion is that I would have expected that you only have gradients acting on
yes,
zeta.
sorry, I know what. Yes, so this is a point that I didn't stress. So the action for restaurant non-gaussianities in terms of pi, not in terms of the original field phi, takes this form exactly. So actually, this is true for any potential, any feature in the limit epsilon going to 0. So you are surprised that you would have expected that the interactions are only coming from the potentials. It's convenient to rewrite it in this form. Of course, you can check that you get the same result. The advantage of this is that, of course, it's compatible with the fact that pi is constant outside your horizon, while in the other formalism is not evident because you have potential interaction. Sorry, I should have mentioned.
But then this will not be the comoving gauge, let's say,
it's so since we are taking the limit epsilon going to 0, Hubble is H is constant, so pi is basically zeta. So it's yes. Actually, it's a nice spin-off of this. So I think it's nice. So it's a completely general form of the action, which is valid for epsilon going to 0, in which you see immediately that out of the horizon zeta must be constant, because even if you have a potential, everything is encoded in this action, and pi equal to constant is a solution.
I see.
Thanks for asking.
Yeah.
So I
Thank you.
should have mentioned.
Okay, let's take the next question.
Hello, thanks. Yeah, I didn't really get which analytical method you are actually using to compute your non-perturbative wave function. So for example, at the beginning, you mentioned some path integral approach, but I would guess this does not apply to the derivative interactions you're then considering, or does it? I mean,
yes. So your question is, I said something about analytical approaches, but then I didn't specify. You're right, in a sense that we are not able to solve basically in any case the full nonlinear solution. Let me stress that the reason is that the compare, for example, if you are calculating some Coleman-De Lucia decay. So in that case, the problem only depends on one direction. Here, there is at least the radius and time. So it's very difficult to imagine to find a full analytical solution. What I mean by analytical approaches is that we were able to estimate the size of the various terms in the limit in which you go to the extreme tail. Okay. And I can enter, basically, you look at the differential equation and you see that there is some scaling when you go to very large zetas. In this way, you don't capture order one, but at least it was a way to predict the behavior on the tail and then to cross-check with the
so it's actually from the nonlinear equation of motion that you get your analytical estimates?
Yes, exactly.
Okay.
So it's an estimate of the importance of the nonlinear terms in the PDE, and what is the behavior when the PDE becomes very nonlinear.
Okay, thanks.
We still have 3 minutes, so I think we can follow the next question.
Yeah, so I'm still a bit confused on what exactly the difference is between what you do in stochastic inflation. It's a bit related to the previous 2 questions, but so, I mean, because the people who do stochastic inflation sometimes, in particular for these models where you break slow roll and you get primordial black holes, that they would tell you that what they're doing is also non-perturbative, right? And that you get this well-known exponential tail So would you expect with your formalism that you would recover also this exponential tail in these models, or would it be?
No, thanks for asking. So these are two very different things. So in both cases, the words non-perturbative applies, but they are very different. So in the case of stochastic inflation, you are resumming the long wavelength behavior. So you're treating the quantum fluctuations as Gaussian, and then you are inputting these in the nonlinear evolution. So it becomes something non-perturbative in this sense, because you are treating some of the effects non-perturbative. Here, I'm just basically, if you want, from that point of view, I'm just studying the noise. So the noise then will feed in. But so when you say that the noise is Gaussian, well, it's Gaussian up to corrections, and here I'm stressing that to know the tail of the distribution is yeah, but yeah, in both cases at the end of the day you get modifications of the tail, but for quite different reasons. Okay, so this is thanks for asking.
So I know you said you haven't done it yet, but would you have a guess of what you would get in these models where you break slow roll? Like, would you think that you'd still get this tail, or would you?
No, the same again. These are different effects in a sense. There are two different. So there will be models in which treating the noise as Gaussian is a good approximation. There will be models in which treating the noise as Gaussian will not be a good approximation, and in this case, these methods must be used. But there is no. There are two different resummation of font.
Thanks a lot.
Okay, let's take one more question before the coffee.
I have a question about how far we are typically in the tail. I mean, what kind of measure how can you typically estimate what does it mean to be far in the tail? This might be important, for example, for the phenomenology, to try to understand if this regime is really accessible or not, what kind of things you can say, because if you have a non-perturbative distribution, what does it mean to be? Yeah,
yes, it's a good question, but it's quite model dependent. So, for instance, let me give you a couple of. So, if imagine that, for instance, you don't have any feature in your so a slow roll inflation model with some additional interactions. As I said here, this is the typical expansion parameter. So when this becomes of order unity, you cannot trust your calculation. So for instance, if zeta is of order 10 to minus 5, you need to go a lot in the tail. Okay. Now, when you produce primordial black holes, for instance, first of all, this typical zeta becomes much larger. Okay. Yeah, so as I said, for primordial black holes, you are interested in zeta of order unity. So in that case, you are interested in this effect if FNL is larger than unity. But it's really model dependent. For instance, in the case of the features, basically, you have to ask yourself whether the Taylor expansion makes sense. But of course, the usual expansion in terms of Gaussian bispectrum will not allow to describe a transition to the other minimum. So in that case, the expansion parameter is alpha square zeta. So the very large alpha, even a zeta, which is just a bit non-typical, will need this correction. So it's quite model dependent. Sometimes, I mean, I don't want to. So for typical models in which there is only slow roll and FNL is small, let me say, let's take the simplest model of inflation, right? Slow roll, single field. Then, in order to see this effect, you should go to zeta, not even of order 1, but of order 1 over slow roll, which is huge. Okay, but it's very model dependent.
Thanks.
Okay, so let's stop here, guys. Thank you for the nice discussions. Thank you also, Paolo, for so many answers. So let's please thank Paolo once again. We'll be resuming at 11:30. Okay, so let's go for some coffee, please. And also, remember there's also the session of the posters. Okay, so you can also, well, please do have a look.
So I'm wondering, how would you assume there is some non-gaussianity hidden in the high end? How can you ever test it? Because already with n equals 3, you have
lots of configurations, and the number of configurations explodes. And you have to do so many tests.
Yes,
Yeah.
I don't know. And this is something that, moreover, I'm not really sure if the correct
Hola. Nice.
Maybe you are only sharing the. Hello, hello. So this microphone works. No.
Hola, hola.
Is Marika here? Marika, sorry. Okay. Testing, testing. Can you hear? Yes. Vale, cópialo ahí. Bueno, el otro lo tengo que tener yo. Sí.
Thanks. Yes. Hello, hello. Yeah. Just put this here. Let me just meet. Doing it again. No.
Well, we after that. That one is making noise. That's why we're. This one.
Yeah, the table.
Okay.
Around.
Yeah. Okay. So.
Hello. Can you hear me? Yeah.
Pero. Ya, pero como hacían ruido, no está. Welcome everybody to the second plenary session of the second day. So we will start with Marika Asghari talking about weak lensing and cosmology with kids. Thank you very much.
Thank you. Okay, hello everyone. Good morning. Today I'm going to talk to you about cosmology with large-scale structures and in particular weak gravitational lensing analysis of the kilodegree survey. So a little bit about weak lensing and in particular cosmic shear, which is weak lensing by the large-scale structures. So if in this picture, you can see background galaxies. And now if the light from these background galaxies passes by massive structures, because of the gravity, its path is distorted. So the image we see of the galaxy will be distorted. Now imagine you have two such galaxies in the background and their light passes by similar structures, creating similar distortions. And that will create correlation between the shapes of galaxies that we see, which is the signal that we measure for cosmic shear. So in order to measure the signal, we need to be able to measure the shapes of the galaxies. But in order to analyze the signal, we need to we need to know how far they are from us. Because the further away they are, there will be more intervening matter and there will be more lensing happening. So we need to know how far they are, and to measure the distance, we use a proxy that's redshift. Okay, so we need two things from the data, the redshifts and the shapes. And then we can infer what's the large-scale structure in between us and the background galaxies, which depends on our cosmology, obviously. Okay, so that was the cosmic shear in a nutshell, but how does it work in practice? So I'm going to give you a little bit more detail so you can appreciate the observational part of it and the full analysis pipeline. Okay, first of all, we can't just look at a pair of galaxies because the signal is very weak. And the only way we can measure this signal is statistically by taking averages over millions and millions of pairs of galaxies, which means that we need deep images with high resolution. We also take these images in multiple photometric bands, so we have colors for the objects in our images. And then we use these colors to divide the images into stars and galaxies, and then create a catalog of galaxies using that. Once we have the catalog, we can measure the two main ingredients that we need from the data. That's the galaxy shapes and the galaxy redshifts. For the redshifts, what we use is, again, these photometric bands that we observed previously. Now, both of these two ingredients need to be calibrated because there is noise in the data and loads of other effects. You can ask me about that later if you want. And they need to be calibrated, and there's a lot of work that goes into this part of it, and it's a field by itself. So each of them is a field by itself. Okay, now what we normally do is divide the galaxies based on their redshift into tomographic bins. This way we can get some information about the evolution of matter. And once we do that, we can correlate the shapes of galaxies between the different bins or within one bin to get our signal. So this signal is normally something like a correlation function. Okay, now we need a theory to compare this with. So you can choose your favorite cosmological model. In this talk, I'm just going to talk about the standards and the CDM model, but it could be any model that you want. Now, your model normally doesn't give you the matter distribution directly, so you need something else on top of it. And you can use analytical models such as the HALO model, or you can use simulations like embodied simulations or hydrodynamical simulations to get the matter distribution. And then using the matter distribution you get from these models, you can model your signal. So you can create something that's like a correlation function. And you have to also model your errors or covariance matrix. But before you can compare these two with each other, you have to take care of nuisance effects. So nuisance effects are anything that's not part of your cosmological model. So it could be astrophysical effects. For example, galaxies might be intrinsically aligned with each other, or it could be data-related effects. For example, this calibration might have some uncertainty associated with it, and you have to model that. Once you have modeled all of these, then you can compare the signals. So the data signal and the theory signal in a likelihood analysis, and then draw your inference, which is like your contours or whatever numbers that you take out of your analysis. Okay, this picture is not complete yet because there's another factor that we have to include, not at the last step though, from the very start, and that is blinding or obscuring the data. So what do I mean by this? I mean that I want to be immune to making choices based on what I want this last step to look like. So what number I want to get out of it. As you can see, there are loads of steps here, and each of these steps have multiple steps within them. And there are choices to be made in each step. Now, you don't want your choices to be based on what value you want, like you like the Planck value, or you like, I don't know, the kids value, or you like some other value. And so you want to make these choices agnostic towards this result. And that's why you need to do blinding. And in weak lensing community, we've been pretty good with applying blinding to analysis in the back. All right. Okay. So now that you know how the pipeline looks like, let me tell you about the data. KIDS, or the kilodegree survey, is a weak lensing specific survey. which means that we have good seeing. So we can measure the shapes of galaxies pretty accurately. And another thing that we have is that we have the Viking survey, which is a sister survey to kids. And together they provide us with 9 photometric bands. And that's a large number for a weak lensing survey, which means that we have a good handle on the colors, which gives us a better handle on the redshifts of galaxies. So we have analyzed 1,000 square degrees of data, which includes 21 million galaxies after all the masking and everything's done. But the survey is completed now, and we have another 350 square degrees of data to analyze, which will be the final data, and which is called Kids Legacy. Okay, so first of all, I want to flash the fiducial Kids 1000 results first, and then I will show you what has happened since. So the fiducial Kids 1000 results. So if you look at this side, this is the cosmic banana. We're looking at constraints on sigma 8 and omega m. The reason we get this kind of degeneracy with cosmic shear is because we can't distinguish between a universe that has a little bit of matter, but this matter is highly clustered, versus another one which has a lot of matter, but this matter is not very clustered. And this is like the generic shape you would get. This is generic degeneracy for cosmic shear. And then you can see this little contour here. This is results from Planck primary anisotropies. Now, because we have this degeneracy, we normally look at this other parameter, which is not shown here. Part of this thing is not shown. This is S8. You can see the definition here. And this parameter is perpendicular to the banana. So it moves, it changes in this direction. And now if you look at this one, you can see that the constraints we have on S8 are comparable to the size of the constraints from Planck. So in this direction, we are comparable. And we had something like a 3 sigma tension. So that was the headline result. Okay, so since then, we went back to the pipeline and look at the different parts of it and to check if we can improve anything and then assess how much difference that would make to the results. So first of all, we looked at the redshifts. So redshifts are notoriously hard to calibrate. For phase 1, we had a certain number of spectroscopic samples for which we know the redshift, and we used that to calibrate our photometric sample, which is just using the 9 photometric bands. Now, since then, we managed to extend the spectroscopic sample, and Jan-Luca van den Busch here has reanalyzed the data using this extra spectroscopic sample. So that's the result that's shown here. We're looking at S8 here only now. You can see the Planck results again here. And then the result I showed you previously is this line, this black line. The fiducial result using this extra spectroscopic sample is shown on top. And then there are 2 variations that are using precision photometric sample on top of it. And these are these 2. Now, the take-home message is that the results don't change very much. And in this case, they actually shift to lower S8. So we conclude that it cannot be the photometric redshift calibration that's causing the tension. Okay, then we went and looked at the galaxy shapes. What if the shape measurement or calibration of the shapes is an issue? Here, Shunsheng Li, he analyzed the kids' data again using an updated version of our shape measurement, which improves on a few aspects. And more importantly, using a more sophisticated set of image simulations, which include multiple bands to calibrate the shapes. And what you can see here, look at this panel, for example. This is S8 versus omega m. If you compare the green contour, which is dotted here, with the gray one, which is the result from this paper, you can see that they are pretty close to each other. Or you can look at this panel as well. So in this case, it shifted a little bit upwards, but again, it is quite a small shift. And from this, we deduced that the shape measurement and calibration cannot be the main cause of the tension. Okay, so if you were in the large-scale structure session yesterday, you've seen some of these results. Simon showed it, but I'm gonna go a little bit more in detail about this. This is a paper where we combine the dark energy survey year 3 results data with KITS 1000. And it was done by a core team that's shown here. And you can see people from KITS and DES were in them. And here you can see also the footprint of DES shown in green. It's like this tank thing. And then you can see KITS, which is these 2 orange bands. On top of that, we're also showing HSC footprint, which is these little purple ones here, because we show the HSC result, although we don't combine with it. Now, let me tell you a little story about this. So when we first started doing this analysis, we thought, okay, this is going to be easy. We just analyze, we just combine them. They are consistent with each other. It's going to be like 2 months max. But it took 1.5 years to finish this project. And the reason is that we soon realized that our pipelines and the choices we made for the theoretical part, so nuisance parameters, how we model the matter distribution and so on, are quite different from each other. And we can't just combine them as it is. Then we thought, okay, what happens if we analyze a mock data set, which is like a has reasonable values in it, once with the KITS pipeline and once with the DES pipeline. And we did that, and you get something like this. So the input parameters are shown in dashed. And then if you analyze it with KITS pipeline, you get this orange contour. You analyze it with DES pipeline, you get a purpley blue one. And this is something like a 2 sigma difference just because of the choices we made for the analysis. So we thought, okay, this is not going to be very useful, especially now that we're combining the data together. We have smaller error bars, so we need to go back and revisit the choices we made for the analysis. So we looked at basically this section of the analysis. So from the modeling of the matter distribution, so this is power spectra mainly, to how we deal with our signal and how we do our likelihood analysis and what we do for our nuisance effects. We didn't touch anything in this shaded area. Okay. All right, so what are the differences? First of all, our priors were different. The priors on the cosmological and nuisance parameters. And then we use different likelihood sampling methods. But I'm not going to talk about these two because their effect is not as interesting as the other ones. So then we also looked at the nonlinear power spectrum modeling, and that was different. And then there is astrophysical modeling. I mentioned intrinsic alignments earlier, but also there's another effect, which is baryon feedback. And we know that, so if you have, say, massive, if you have AGNs in your galaxy, they create these jets and pushes matter around, which can change your matter distribution on smaller scales. And how you deal with this was also different between the two pipelines. Okay, so let's look at the modeling of nonlinear power spectra first. So here you can see matter power spectra. You can see the linear matter power spectra in black, And then the nonlinear models, one that's used in DES, was used in DES, which is called HaloFit, and then one that was used in kids, which is called HM-Code 2016. And you can see that in this kind of plot, they look like they are right on top of each other. You can distinguish them. But once you look at ratios, you can see what's happening. So in this one, we're looking at ratios of each of these kind of halo model style nonlinear power spectra to an emulator. And this is taken from Mead et al. We looked at, we compared it with Euclid emulator, but this is a different emulator, but it shows the same kind of trend. So you can see HaloFit and HM-Code 2016. But since we did the analysis for these two surveys, HM-Code 2020 came out, which is more accurate. And I don't know if you can see, but the variation you can see here is within 5%, while both of these cases, it goes beyond 5%. So we thought, okay, we just take the one that is more accurate. So that was the choice for our hybrid analysis. Then we looked at nuisance parameters. So the first nuisance parameters that I'm going to talk about is galaxy alignments. So here, remember this picture. Now imagine you have galaxies that live nearby some of these massive structures. And because they live there and they were formed near there, they're going to be aligned with the tidal field around this matter distribution. And this creates a signal that can be confused with cosmic shear and has to be analyzed. And if you want to divide it into different factors, you have this one, which is cosmic shear. So it's the background shear that happens. Then you have this one, which is your intrinsic alignment. Then you have one that is the combination. So there's a galaxy that lives near this matter. It's aligned with it. Then you have a galaxy in the background that is being sheared by this matter. So you get an alignment between this background one and the foreground one, and that's called gravitational intrinsic alignment. That's why it's called GI. Now, if we look at how this was modeled in kids and DES, that was also different. So in kids, we used the NLA model, which is an empirical model that's been shown to be a relatively good fit to data. In DES, they used the TAT model, which is a perturbative model that has more freedom compared to NLA. But for the hybrid analysis, we decided that we don't have enough data to be able to constrain the TAT parameters. So we go with NLA, but we added extra freedom in it by allowing for a redshift dependence there, which wasn't there in the kids analysis. And then the other nuisance effect is baryon feedback. Now, in this plot, you can see ratios of power spectra from hydro simulations to gravity-only simulations. And you get this kind of dip because of the baryon feedback. And depending on how strong your feedback is, you get a deeper dip. So what the way the two teams dealt with this effect was also different. So in kids, we marginalized over a baryon feedback parameter, which is kind of incorporated in the nonlinear modeling already. And then in DES, they took the approach of doing scale cuts and removing basically all scales that are around here that are affected by this effect. Now, for the hybrid analysis, we chose a hybrid method. That was to use scale cuts and also marginalize for any remaining residuals that might be in the data. All right, so, and this is the final result. So we have S8 again. This is the Planck data point. And we have the combined kids and DES analysis using the hybrid pipeline that I told you about just now. And that's this pink one here. If we only analyze the DES Y3 data, we get this data point, and kids 1000, we get this one. And you can see that they are within about 1 sigma of each other. We also asked some of the HSC members to reanalyze their data using our hybrid method because their results came out while we were finalizing the paper. And they did that and they got these 2 results. And you can see that all of these are very consistent with each other. And if you look at the pink one, it's no longer really in tension with Planck. So it's 1.7 sigma. So is it done? No tension? Finished? All right, so some people might see it like that, but there are some things that are a bit curious. And we looked at a few variations of the hybrid pipeline. And in particular, one of them that I want to show you is this one. So intrinsic alignments of galaxies are difficult to measure for the galaxies that we have. So we don't have like a direct measurement of it. So we don't really know which model is more accurate. Also from simulations, it's not easy to measure this. So if we reanalyze the data using the NLA without Z, that's the method that kids used, we don't get any shifts in the result. But if we choose TAT instead, which allows for scale dependence of the alignment, which will be fitted to the data, we get a shift, which is about 1 sigma. And then we get to something that is looking a bit more like tension, depending on where you want to put your number. And we don't know what is correct currently. So maybe there is still some hope for people who like tension. All right. Okay, so this is my summary of the kind of fiducial results from recent weak lensing surveys. You have the Planck data point here for reference. And then the green ones are the DES results. So DES, we had huge error bars because it didn't have very much data. And then you can see how it changed with DES year 1 and then DES year 3. And then we have the HSC results, which have been pretty consistent. And then we have the kids results in orange. And then finally, we have our combined result, which has, you can see here, it has quite smaller error bars here. So we've always been consistently on one side of the Planck data, and that I think is kind of interesting. Also, it's interesting that it's on this side, not on this side. The reason that's interesting is because most systematics in the data would add power. And if they are not taken into account, it means that we will overestimate our S8 result. So this is something just to think about now. Okay, now in my last 10 minutes, I want to talk to you about what plans we have for Kids Legacy. So for Kids Legacy data, the cosmic shear analysis of it is going to have 350 square degrees extra data. That will translate roughly to a 17% reduction in the error bars on S8. And we have a possibility of adding more galaxies that we didn't use before that are at higher redshift if we can calibrate them. But we think we have better calibration simulations now, so it might be possible. And that could be an extra 35%. So we could get error bars that are maybe even 50% smaller than what we had for Kids 1000. But this has an asterisk. We're going to have 2 shear measurement methods instead of 1 that we had before, which allows for consistency checks. And we have multi-band image simulations that I showed Xunsheng's results before. And then finally, the thing that I'm really excited about is a kids-only combined probe analysis. And by that, I mean the 3x2 PT analysis. So 3 2-point functions, cosmic shear, galaxy clustering, and galaxy-galaxy lensing. And this has been a very popular combination because it can break degeneracies. Okay, so when we look at the kids data, if you look at the kids footprint, it's quite small. So if you want to get any galaxy clustering information out of it, you have to be able to push to smaller scales, and then quickly things become nonlinear and you have issues with galaxy bias and so on. And that's where a lot of people who work on galaxy clustering don't like to go to. But we like to go there, and we have gone there. So how do we do that? We can use Halo model. So Halo model, the assumption is that all matter is in halos, usually assumed to be spherical. And like in this one, you can see a simulation here of a cluster. And then in the second panel, we make it halo modelized. So we make them spherical. And then if you know how these halos are distributed, so how many halos of which mass you have, and you know the halo profile and how the halos trace matter, so halo bias, then you have everything that you need to know to create your power spectrum. And then on top of that, if you have a tracer, for another tracer for matter that populates halos, for example, galaxies, as long as you know how these galaxies populate halos, you know how everything is connected to each other. And this last panel is, for example, showing the galaxy distribution that you would expect based on a simple halo occupation distribution. If you want to know more about halo model, we've written a review recently, so I like to point you to that. And it's mainly aimed at cosmologists, so everyone here. Okay, so one thing that, let me see how much time. Okay. So one of the things that Halo model has issues with is modeling the transition region. And by that, I mean the 1 halo to 2 halo region. So when you want to model power spectra, you can divide it into a 1 halo term, so all correlations within 1 halo, plus a 2 halo term, correlations between 2 halos. And then you can add them up to create your power spectra. And then if you look at the ratio of this power spectrum to some emulator, for example, here, I'm using Dark Quest, you can see that the ratio is not great. So sometimes it can be 20 or 30% lower. In this case, it's not so bad, but it can be worse than this. And then recently, there's been a prescription for making this a little bit more accurate by adding a nonlinear halo bias. So normally we assume that halos are linearly biased with respect to matter, but we know from simulations that's not true. So if you add this extra ingredient in there, you can remedy this issue with the transition region. And like here, for example, this line here is showing when you add this extra term in there. And then we are within the error bars of the emulator. Okay, so in this paper, Constance Mahoney looked at this effect and seeing what happens if you do your analysis on a mock data that we know where the input is, but you ignore this nonlinear halo bias for a kids-like survey. And you can see the inputs are given in dashed. If you analyze with your linear bias, you get this orange contour. If you add an extra freedom to the halo term to move up and down, you get the green contour. And then you add extra information about galaxies, you get the red contour. And all of them are biased in one or both parameters. So it's very important to include this in your analysis. And then a follow-up to that was the analysis of real kids data by Andrei Dvornik. And here we're using kids-only data, but only combining galaxy clustering and galaxy-galaxy lensing with galaxy abundances. So it's not a 3x2 yet, but this is kind of the precursor using kids 1000 data. And here you can see the cosmic shear results on pink as for comparison, and the Planck results in black for comparison. And then the blue is the results from this paper. Here we're using the Kids Bright sample, which is similar to the gamma spectroscopic survey as our lenses, and all the kids sources for our sources. And we were pushing to quite small scales here. So that's why we can get the same amount of information about S8 omega M as an analysis of the clustering in BOSS survey, which is 9 times bigger area compared to kids. So I think this is a very promising venue for getting more information if we can model the small scales. And this is just a visual way to show how much bigger BOSS is versus kids. So this blue sections are BOSS, and then the pink ones are kids. And you can see that it's quite a lot smaller, but we have the same constraining power. All right, so I'm gonna summarize and conclude now. So cosmic shear analysis results are consistent with each other, and they still show a value of S8 that's smaller than Planck, although the tension, if you look at just the kids plus DESI data, has been removed or reduced, at least. If you want to combine data from different surveys, you have to do extensive analysis beforehand. I really recommend that you do a lot of mock analysis before you do your real data analysis, so you understand what your modeling is doing. And then we also need to understand astrophysical effects better if you want to look for new cosmological, like physics, new physics in cosmology. So we can no longer think of galaxies as just basically stickers on the sky. They're actual objects with their own lives. And then finally, stay tuned for Kids Legacy analysis and results, and the kids only 3x2 PT analysis. Thank you.
Okay, thank you for a nice talk. So we have time for questions. Yes.
Thank you for the talk. If in the case for the 3x2-point analysis with the using just the kids survey, how are you going to do the sample selection for the galaxy clustering? Is it going to be the same sample as the weak lensing one, or as a sample?
Oh yeah. So the sample that we're using here is the Kids Bright galaxies, which are much brighter than the weak lensing sample. So it's quite different to the weak lensing sample. The reason we're using these galaxies is because we can calibrate the redshifts much more accurately, because we have the gamma survey that has a lot of overlap with kids, and it's very similar to the bright sample. So we can, and that's a spectroscopic sample. So we can kind of find the photometric redshifts accurately.
Thank you.
Hi, thank you so much. It was a very interesting talk. I'd like to ask you about the inclusion of nonlinear halo bias in the analysis. If in practice, what you do is run an emulator at every iteration step of the MCMC process, for example, because I gather that must be very time consuming. I don't know if that's what you do in your analysis, or if there's any work around about this.
So that's a good question. So for this paper that you see here, that's what we did almost. So we used MCMC, and we because the nonlinear halo bias is not very sensitive to cosmology, we updated it every 20 steps or so of the chain. But for our final analysis, we are thinking of ways of speeding this up. by using emulators that are much faster. For example, Cosmo, you've heard of that. It's a neural network emulator. Or we are also working on analytical solutions for it that will make it much faster.
Thank you for the talk. In your conclusions, you said we need to understand astrophysics better. What if we understand astrophysics good enough already, and we just have to live with the fact that the galaxy formation is a stochastic process, and you cannot pin them down better than we have now? We understand quite good galaxies. What then?
So I think, of course, there is quite a lot of information about galaxies already, but it's not been connected to the cosmology level that we need, because people work in kind of separate fields normally. Like galaxy people are more interested in galaxies as galaxies, and we're more interested in them as traces. And it's kind of like one reason I think is also simulations. So I think soon we'll have some simulations where the resolution is high enough that you can resolve galaxies, and they will have large enough volume, so you have a cosmological volume, so you can do cosmology with it too. For example, for intrinsic alignments, we need a big sample, so we can actually measure it in a statistical way. So you can beat on the stochasticity, basically. So I think there is still things to do. I don't think that we're there yet. So yeah, and I'm actually excited about these new hydro simulations that can answer these questions.
There was one question over there. I think someone.
So it seems to me if I want to go to smaller scales, I need to model the halo bias non-linearly, and then the galaxy bias non-linearly also follows, but then also what baryons are doing to the matter power spectrum. And I was wondering if you could tell us a little bit about how those things are related to each other. Is there an interplay between them? Is one of them worse to worry about than the other? So how does this work?
Yeah, this is definitely interplay between them. But which one's worse, this depends on which probe you're looking at of the three of them. So for, say, weak lensing, we definitely care about baryon feedback a lot. But for example, here in this paper, we also include a parameter that allows for satellite galaxies to feel the effect of baryon feedback, so their distribution to change based on baryon feedback. So that's on top of the baryon feedback parameter that you include for weak lensing. So you can include all of these in a consistent way within Halo model, and that's another reason that we like to use Halo model to model all of these effects. But say, for example, intrinsic alignments of galaxies, they're not important for galaxy clustering. So it depends on which one you're looking at. And that's one of the reasons they're very complementary, because they're sensitive to different effects.
One question here.
Thank you for the very nice talk. Can you elaborate a bit on the blinding strategy that was used in kids? Like, where do you blind, where do you unblind, and whether it was different from DESI?
Yeah, sure. So the blinding strategy in kids, we've used a few methods in the past, but the current method we're using is at catalog level, because we thought that this is a bit harder to unblind. And what we do is that we create 3 catalogs. One of them is the real catalog. The two others are fake, and they're within 1 or 2 sigma of the real. We don't know what the order is. And someone else outside of the collaboration keeps the key to it. So for Kids 1000, it was Matthias Bartelmann, for example. And then basically we kind of write the paper, get all the results, analysis for all the 3 blinds. This is an example of it here. And and then so we had an unblinding party 3 weeks before submitting the papers, and that's where we showed this result. And Matthias Bartemann told us after a lot of deliberation which one is the correct one. So we kind of like, basically we send all the results to him so he knows that we're not going to change anything once we know the result.
Yeah, go ahead.
Thank you for the nice talk. Can you talk a bit about the impact of tomography here, since you talked us through all of the effects, right? So is it most relevant at the lowest redshift bins? Is that what's driving your constraints, or in the DES plus kids?
In the DES plus kids?
Yes.
So we don't change the tomography in DES plus kids. It's the same as what the two surveys chose. But in general, if you don't have tomography, it's you lose some information because, for example, if you have low redshifts, that's where you get most of your intrinsic alignment constraint. But if you have everything together, then everything is washed out. So you don't get that. And I don't know if I have a product yet. And you can see here that signal changes as you go from low redshifts to high redshifts. So this is like combinations with low redshift. This is combinations with high redshift. But we're not super sensitive to redshift in recleansing. That's why we don't need to create like tons and tons of tomographic bins. Usually a few is enough to capture most of the information.
But you didn't play the game of like throwing out low redshift bins.
Oh,
it seems how stuff shifts. Or...
yeah, so for kids plus DES, we didn't do that. But within kids and DES, we have done that separately and shown that it's all consistent. Yeah.
Okay, quick one, last one. There, okay. Any plan of doing a combined 6 times 2PT analysis with CMB lensing? That should really help with a lot of this nuisance that.
Oh, with CMB lensing. So we have another 6 times 2, which is a photometric and spectroscopic samples. There is a group in kids that's working on that very hard now. It's quite hard to do it because that uses the same sample for the lensing sample as in weak lensing sample. With CMB lensing, we have combined with CMB lensing previously, not in a 6 times 2 in particular, but like cross correlations or just like simply combining with CMB lensing. Thing is, the kids team is quite small, so we are kind of people power limited. But if other people want to work on that, you're welcome to contact us, and we're happy to work with them.
Okay, so thank you very much for the nice talk and the nice answers. Hello. Hello.
Hey, is it working?
All right.
It's fine. Okay. So next we have Maria. Yeah, so we have Eva Maria Muller from the University of Sussex, and she will tell us about galaxy clustering and, well, the dark-energy spectroscopic instrument.
All right. Thank you very much for having me. So this is largely a talk about galaxy clustering in general, but because of the timing, I will focus a lot on the dark energy spectroscopic instrument. So part of it is on behalf-ish, the DESI collaboration. All right, first a disclaimer, we are not the DES, we're DESI, and that is important. We are the dark energy spectroscopic instrument. However, our telescopes are actually twins. So on the left, you can see the 4-meter Mayau telescope at Kitt Peak in Arizona, equivalent to, so it's really a twin to the Blanco telescope in Chile. Indeed, some of the targeting surveys, the decals, for example, was done with the Blanco telescope in Chile. All right, so what's the difference? So here we have a 3D data cube. And the importance of the spectroscopic here is really that we get really, really accurate redshifts. So not only do we get the position of the galaxies on the sky, but really 3D information along the line of sight. Unfortunately, that means we don't have as many pretty pictures to show as all the photometric surveys, only spectra. But we do have the advantage that we get the precision, much higher precision on the redshift compared to the photometric surveys such as KIDS or DES. All right, let's start with the smashing of records. So DESI already has produced the largest 3D map of our universe. The previous record holder was SDSS, but even after only a few months of DESI, we could improve upon this record. So already having observed millions of spectra of galaxies, quasars, and so on. Another record, I think at least it must be, but the highest number of redshifts in one night. So you really need to let that sink in that we have 140,000 spectroscopic redshifts in just one night. So maybe for those of you that are younger, that might mean nothing, but it's really incredible compared to how things used to be, is that we're now in one night, we're talking about hundreds of thousands of galaxies and redshifts that we can observe. One of the main reasons why there's such an improvement is really that DESI has this 5,000 eyes, or this 5,000 robotic fibers that allow quickly, within a few minutes, to switch between exposures, or we call it different tiles. So you can really reconfigure the entire focal plane within 2 minutes. All right. Yeah. So here, just give you an idea, a bit of the instrumentation. You can see here the light goes into the primary mirror, then gets reflected and gets to 6 lenses. Oh, it did not stop. Okay. So here you can see one of the lenses that allows roughly 8 square degree on the sky, so roughly 38 times the area of the moon. And on top you have the focal plane, where you can now see is you have those 5,000 fibers and 5,000 robots that can rotate to specifically target a galaxy quasar on the sky. That light then from the fibers goes down to 10 different spectroscope, that gives us the nice spectra that I showed you earlier. All right. Remembering the good old days where actually undergrads had to drill and plug these. So here's a video. What needed to be done for SDSS before we had these robots. And you can imagine how time intensive this is, not only the plugging, but then also somebody physically had to shove these blades under the telescope, right, to get your spectra. So this is why now, now that we have those 5,000 eyes with DESI, we can really, it's really order of magnitude difference. Right, but of course, DESI didn't start in a vacuum. It's already a legacy of many successful galaxy surveys. Started, for example, with the CFA, with Harvard only observing 1,800 galaxies. And now you can see here in the plot, and I hope you appreciate that is a log number density plot here, how much more galaxies we're now observing with DESI. And similarly with Euclid. So we're talking really about millions and millions of galaxies with very, very accurate redshifts. All right, in particular, SDSS was really important for DESI. Indeed, DESI, once upon a time, was called the Big Boss Survey. So an extension of the Boss Survey. Fundamental for all of this, for the Galaxy Survey, is of course the idea of having standard candles and standard rulers. So a similar concept to how you use supernova for cosmology. So what if we know an intrinsic property of whatever you're observing, then you can use it to trace the expansion history of your universe. And in particular here, what we can use is the baryon acoustic oscillation scale, so the BAO scale, that you can equally see in the CMB. And for his work on large-scale structure, Peebles a couple of years ago got awarded part of the Nobel Prize. All right, just a reminder what BAO actually is. So in the very early universe, you have the coupling between baryons and photons. So you get these acoustic oscillations where you have gravity pulling and pressure pushing, that giving you the waves. And of course, you don't just have one peak, you have many overdensities, but then overall creating this ring within the large scale structuring for our galaxies. So we can use, while by eye it might not look as the scale, as a preferential scale in there, we can analyze that data really using 2-point statistics, so looking at the excess of clustering in the clustering of galaxies. And what you find is this peak position in the 2-point statistics. So either in the 2-point correlation function in configuration space or in Fourier space, you will see those wiggles that are due to the baryon acoustic oscillations. So so DESI, but also BOSS and previous surveys were really designed to measure the BAO scale to percent level. All right, so what we then can measure, we can now split it up in the direction along the line of sight or just across the sky. And what you will get is along the line of sight, you will get constraints on the Hubble expansion, and from differences in angle of the BAO scale, you will get constraints on the angular diameter distance that we then can use to constrain cosmology. All right, I mentioned it before. This is really a legacy from SDSS and from BOSS. And you can see here just the progression of the BAO measurements within the past 20 years, really. SDSS was operating for the past 20 years and finished in 2019. SDSS was really a journey of firsts. So for example, we had the first detection of the BAO peak. To be fair, almost simultaneously, 2DF also got a detection in Fourier space, but I'm still claiming it for SDSS. It was first detection of the BAO signal in the Lyman alpha forest, first detection of the BAO signal in the distribution of quasars. And while SDSS was largely a journey of firsts, I think DESI will be not a journey of firsts, but still a journey of records, so a journey of the largest of everything. So to an extent, SDSS was really a testing ground for DESI, making sure that we really understand what we're doing. All right, so just to give you the basic information, what actually is DESI? So as I said, it's a spectroscopic survey planned for 5 years. We have 5 different targeting classes. So we have at low redshift, we have the BGS survey, so it's the bright galaxy. And then higher redshifts and intermediate redshifts, we have emission lines and we have luminous red galaxies. And then at the highest redshifts, we have quasars. And we also, so we're using the quasars as just a tracer in the same way we're using the ELG and LRG, so as a point source, but also we're using the quasars for the Lyman alpha forest measurement. So it will be a 14,000 square degree survey covering roughly 1/3 of the sky. All right, so if you want to know more about Lyman alpha, there is another talk, I think tomorrow, given by Andre in P8. But I like this slide because here you can really see this is a forecast and you can see the unprecedented level of accuracy you will get on the Hubble parameter across redshift 0 up to 3.5. And if you wonder why there's a bit of oscillation in the error bars there, well, that's because we have 5 different tracers, right? So and for each of these 5 different tracers have different target selection, different number densities, so a different error bar. So this plot shows you the combination, all of these different tracers, but implicitly you can see the error bars going a bit larger between 1.5 and 2, where it's a transition between the ELG, LRGs and quasars. All right, also to highlight that because we now do have the BAO not only at the low redshifts, but also at the high redshift from the Lyman alpha, you can get a really good constraint on omega matter, so the matter of the universe, which you can't get just by using Bose clustering, for example. You really need the low redshift in combination with the high redshift to break degeneracies to get a constraint on omega matter. So for more details on Lyman alpha, go to Andre's talk. The timeline, so the main survey started 2 years ago in 21. And so this is a slide actually from our summer DESI collaboration meeting, where you can see we already collected all the data for our year 1 release. We're currently collecting data for year 3. And the first, so the DR1 analysis should come out hopefully early next year. I think our internal deadline is around March or April next year, where we should have the cosmology constraints from DESI. All right. So here you can see the progress. This is from last year, so this is all that will go into our DR1 analysis. And you can see that we already have almost 10,000 square degrees. Here, the fraction and coverage, we're overall going to have 5 passes over each galaxy. So what it means is we don't have 5 passes yet for all of the targets here. So some only have 1 pass, a lot already have a 2nd pass, and so on. But you can also see DR1 is roughly 1/3 of the entire survey, so 28% of tiles that are already completed. Now, this is how it looks already this year, so summer this year. We are almost halfway through as far as getting the data is concerned. So we are done up to 46%, covering an area of 12,000 square degrees. Now, you might have noticed it's a dark there. In general, our survey is split up into a dark survey and a bright survey, just depending on your observing conditions. So if the conditions are not that good, it's part of the bright survey, and for the ELG, LGs, and quasar, the dark survey. And indeed, if we actually project our progress, we will actually be done ahead of schedule 1 or 2 years. What I mean with that, the bright survey is what you can see in orange. And if it continues like that, we should be done next year, April next year. So there's talk about year 3 probably already containing the entire bright galaxy sample. You can also see it if it continues like that. Also, the main ELG, LG, and quasar sample will finish a year earlier. So what I actually said earlier, that DESI is a 5-year survey, well, it looks like the main survey at least will be done in 4 years, which is good news because most likely there's going to be a DESI 2, right? We already have the telescope, we have the instrument, everything is working very smoothly, so it's likely the DESI will get extended. And not even a fire can stop us. So this was very traumatizing, where we had the Kitt Peak had to shut down because of some wildfires. And this is actually, the lower part is taking from the camera, from our instrument, right? So you can actually see how close that was. And I can personally remember a night where I kept just refreshing to see until at some point the camera gave off and it was just black, and we had to wait for another day before we actually knew that things are fine. And indeed, we knew it was coming, so it was shut down. So it seems like there was actually no damage at all. We had a bit of downtime. Without this downtime, we would have been done even earlier, but it's okay. All right. Earlier this year, we already had what we called the DESI early data release. So what this means is before we started our main survey, there was a phase of a couple of months, which we called survey validation. So this was largely to check that our targeting algorithm works and that the instrument and everything works as it should be. And after that was done, and with a bit of tinkering, we then went on to something called the 1% survey. So we basically, it was a test run for 2 months where everything was the way it is now for our main survey. And all of this combined was publicly released, I think last month. Yeah, should be last month. All right, so the 1% survey is really what it says, 1% of DESI. And so you have all the different traces, ELG, LNGs, and quasar, and so forth. And you can use it for your science already. So here you can see the number densities. Again, what I said earlier, you can see the different classes that we are targeting. With the quasars peaking around, is that 1.8 or something like that. And then you have the lower redshifts. The difference there, you can see a bit of the gray and the full is just the difference of what was targeted as, let's say, a quasar and what was actually then confirmed as a quasar. So overall, we're doing very well, and everything is really as we hoped it could be, even more so, exceeding expectations, really. Indeed, only with the first 2 months of DESI, so this early data release, we have a several sigma detection of the BAO bump in the LRGs, but also in the bright galaxy sample. So you can see here on the right, is the correlation function for the LG. Again, you can clearly see the bump. And it's really amazing to see after only 2 months of data that we have already a detection of the BAO signal. All right. Of course, we not only want to measure the BAO scale, we want to use it to constrain cosmology. But it's good to keep in mind where I showed you earlier, we are not directly measuring H or DM. What we're really always measuring is the combination of you. So you have your sound horizon here. So what we're measuring is a sound horizon times H, or sound horizon times your angular diameter distance. Which is why from BAO alone, for example, you don't get a constraint on H0. You really need to add in some information from BBN or some other prior on the baryon content to break this degeneracy. So this is a plot from SDSS for the final data release. All right. Beyond BAO, let me share a few secrets. To be fair, it's actually not a secret. I just would like to use the platform just to highlight a couple of things. And one of them is that usually when people write constraints on BOS, this is not purely a constraint on BOS or large scale structure. Usually hidden in this is in some way or another, people are using BBN, either by directly putting it in or by assuming a prior on your baryon density, or a prior from CMB even. Secondly, also quite often NS is fixed to its Planck value, or sometimes varied, but varied within a prior that is constraining. Because I said earlier, the BAO really doesn't give you constraints on H0. So this is just a bit of word of caution to look closely if you're comparing different analysis. Sometimes if you see differences, it basically boils down to what have people assumed about baryons, what have people assumed about NS. The second secret that actually should really not be a secret is that we're doing a Bayesian analysis, right? And unfortunately for Bayesian analysis, we have priors, and priors can matter. In particular, if your data is too noisy to constrain the model that you want to constrain, you will get effects of those priors. And in particular, if you not just want to do a BAO analysis, but direct fits, where you directly fit lambda CDM to your 2-point correlations, then these effects start to matter a lot. And it's not a secret because it has been pointed out by a couple of people in the audience. And the way to get around this, you could ditch the Bayesian analysis and go full frequencist. Or of course, use DESI data. All right, but for that, unfortunately, you need to wait. While we're in the middle of that analysis, unfortunately, I'm not allowed to show you that data. But what I wanted to highlight is, if you're confused why there are so many different measurements of S8 or sigma 8 coming from galaxy clustering, then this, I think we understand it quite well. So this is a plot by Mark Maus et al. So a couple of DESI people that looked into this more closely. Roughly speaking, there are two effects. One is the assumptions about your priors, in particular your nuisance parameters. But on top of that, there is a bit of a difference in methodology, whether you use template fitting or this direct lambda CDM fits. So in general, what you will see is studies that use the template usually have larger error bars. And they have larger error bars because it's model independent, right? So you don't assume lambda CDM. Because of this model independence, your error bars slightly blow up. The second is that the Alcott-Patinsky parameters are degenerate with F sigma 8. And this because the template fitting, you usually assume that they're independent parameters. You can't really catch that. What happens next is that actually in BOSS, the third redshift is a bit funky and is pulling it in a direction that is disfavored by lambda CDM. So overall, you get this spread in different values that you see here in sigma 8. But what I want you to take away from this is that I think we quite well understand where it is coming from. And overall, currently testing within DESI the effect that all of these have. And generally speaking, is not as much of an issue for DESI because our data is just a much better quality or much larger signal to noise because we just have so much more data. So all of these prior effects will matter less and so on. And there is another DESI talk at this conference by Jan Lai on Friday in the section P12, where we'll talk a bit more about validating some of our pipelines and comparing some of these template fits. There it's called shape fit, which is developed by Hector Gilmarine and collaborators, is a bit of an extension of the standard methodology that was used by BOSS and eBOSS. Or what's called full shape here is sort of meaning the direct fits, where you just use your 2-point correlation functions directly then to fit your lambda CDM model. So if you want to know more about the whole topic, then go to this talk. All right, continuing with a bit of advertising. Rafaela, my student, is she is leading the analysis of extensions to the early universe to solve the Hubble tensions, and is currently, hopefully, about to publish a paper using all the eBOSS data. So if you want to more know about that, you can go to her talk. It's also on Friday in the afternoon. So here again, using full shape or direct fit approach to constrain your extended models to explain Hubble tension. On a less positive note, sadly, Nick Kaiser passed away this year. A lot of his work has become so ingrained in the large-scale structure analysis that it has become standard textbook. But here, just wanted to highlight one of his key paper pointing out the difference between in real space and redshift space that gives you what we now call the redshift space distortions, or sometimes called the Kaiser effect, right? So you get the squashing in your distribution of galaxies. But this is just one thing that he did. Many, many other papers. I recently even discovered that just the whole idea of that galaxies are biased tracers because they're sitting in the peak of a distribution goes back to Nick Kaiser. For me, and this was just so standard already because I've read it in so many textbooks that I really wasn't aware that it goes back to a paper by Nick Kaiser. And also, if you ever used clustering data and came across an FKP weight, well, the K is Kaiser. All right. Moving on to a bit of work I was doing recently with some of my collaborators, Ben Cullis and David Parkinson, was looking at, well, can we also use the largest scale to constrain cosmology? So not only use the BAO or redshift space distortions, but using really the peak of your matter power spectrum. And you can see here, this is an old plot from Planck, where the galaxy clustering basically usually always stopped at K at 0.02. So before you can actually see the peak. And indeed, the largest volume that we have, largest 3D volume, is from eBOSS, from the quasar sample. But even there, we actually cannot really detect a detection of the turnover point, which is a really fundamental quantity. So what we're also currently trying to do is DESI It's just really exploiting all of the scales, pushing to larger and larger scales, right? So here to smaller and smaller K values. So it can really trace the full scale of the matter power spectrum and not just this intermediate range of K values. Why do we want to do that? Well, sorry, the matter turnover point gives you information on the matter radiation and quality. So the idea is really to use the peak of your power spectrum as a standard ruler in the same way you can use the BAO bump as a standard ruler. And it will contain constraints or information on H0 and also on omega matter. So what we did is we used the Poole et al. Parameterization where you parameterize your power spectrum with two slopes, and then used the EBOS quasar sample. And while we do have a measurement of K equality, unfortunately, we cannot really claim that we detected the turnover point. So it's still within a flat power spectrum at a larger scale is still within the error bars of our analysis. But in principle, on the right-hand side, you can see how you can use the turnover point for cosmology. So here TO stands for turnover point, and TO plus BAO, here it actually really is without any BBN constraint. And because here with the BAO, as I said, we can use the low redshift and the higher redshift BAO to get in constraints on omega matter, then use to break the degeneracy, use the information on the turnover point to break the degeneracy between omega matter and H0. So get a constraint on H0 that is free of sound horizon, if you will. And what's really unique about our analysis is that we're really trying to localize the peak here in the same way the BAO analysis is localizing the BAO bump. All right. And lastly, in the larger scales, of course, we can also try to measure primordial Gaussianity. So here, this is from a recent paper by Mehdi Razai. This only shows constraint on 2-point statistics on the power spectrum. And you can see how our constraints get closer and closer to the ones in Planck. And hopefully, within DESI 5 year, we hopefully will get close or to be competitive with the Planck constraints. It is a very, very hard analysis though. All right, so stay tuned. By next year, Cosmo 24, we should have the first cosmology results coming up from DESI. And of course, I also, on behalf of DESI, just would like to congratulate the Euclid collaboration for a successful launch earlier this year, and even having nice first data from its commissioning. So unlike DESI, Euclid's going to have both the lensing component and the spectroscopic clustering. So it's really a combination of the weak lensing and the clustering. On the left here, you can see the VIS instrument. So this will give you your photometric survey, and the right-hand side is from the NISP in the Grizzin mode. All right, and I will end here.
Thank you very much for the nice talk. So we have plenty of time for questions. Use this one. Hi. So what are DESI plans in terms of multi-trace and analysis of the data? Is there plans to perform that, or plans at the moment just to split in BGS, LRGs, and ELGs, and non-overlapping redshift beams? Can you comment a bit on this?
The answer is Oh, sorry. The short answer is yes, we're going to do multi-tracer.
Hi, thanks for the talk. So you mentioned template fitting versus direct lambda CDM. What should we expect from the first analysis of DESI? What's going to be the fiducial result? And why?
Ooh, you're getting into politically tricky territory. Yeah. I think the short answer is we're doing both, because I think the value in both. Because what is nice with the template fitting is you can really isolate where your information is coming from, which you can't do when you have your direct fits. So if you really want to know where your information is coming from, particularly thinking of consistency tests or things like that. So for that, we're definitely going to do a template analysis, but we're currently working in parallel to also have the direct fits. Which ones will be the numbers that will be cited in the abstract? Honestly, probably whatever is tighter. But I guess to be discussed.
Yeah, just a follow-up. Do you also do any blinding?
Yes, we do blinding. There are a couple of papers out by Samuel Bryden and also Hector Gilmarine. It is done on a catalog level, so not on the 2-point statistics. And it's generally, you're shifting around your redshifts to blind your data. And there was a lot of testing that was done to apply this blinding algorithms to mocks to make sure that we're not messing our data up by the blinding. So the current pipeline is the first stage is all methodology is tested on the mocks. Then we're going to start working on the blinded catalog, or indeed started working on the blinded catalog. And then we're going to unblind in the large stage, in the last stage. And this blindings, the different sorts of blindings. For example, we have a BAO blinding, but we also have an FNL blinding because we're talking a bit of different scales. So the answer is yes, and multiple people working on the whole blinding procedure.
Thank you.
Thanks, very nice talk. So I was curious about the matter turnover point on that project. So is it like you are fitting or you are looking for the peak position of the matter power spectrum, and that changes with the ratio of the matter component and the radiation component, which is sensitive to that?
Yes, exactly. Yeah. So the position of the peak, so the what we call K equality, depends largely on H0 and omega matter. So we're trying to really just measure what K equality is, and then in the same way we are measuring where the BAO bump is, and then using this scale as a standard ruler.
Is it like theoretical prediction that K is in proportional to H0 to omega matter?
Sorry, can you repeat?
Is it like theoretically like the peak position of the matter power spectrum, which at the peak, the first derivative will be equal to 0, and then you derive that?
Yes, yes. So lambda CDM, yes.
Okay, thank you.
Thank you very much for the nice talk. I was wondering, for the template-based analysis for beyond lambda CDM or adding massive neutrinos and the standard deviations, are there plans to check that they actually can recover unbiased results for the cosmological parameters, or you just...
Yes.
Okay.
Lots and lots of testing with mocks and simulations is going on.
Yeah, perfect. Thank you.
I'd like to ask some more about the thing you said about the priors becoming less important because the data becomes more constraining. So you also have the effect that you have to expand your model complexity, right? If your data is more constraining. So you have more nuisance parameters.
So can you give some more intuition why this works? Why the prior volume effects become less severe?
Sorry, your question is, sorry, can you just repeat and speak a bit louder? Sorry.
Sorry. So you know, your data become more constraining.
Yes.
So usually you also need more nuisance parameters, for example, in the EFT, right?
Okay. Well, I think it's partially our information on the shape is going to become much better. So some of these degeneracies will be just tighter constraints. It kind of depends on the nitty-gritty details of that you're asking.
Okay.
Any other question?
Thank you for the very nice talk. On the EDE constraints that you showed, so for this particular model that was considered, are you fixing the other two parameters of the EDE model, or they are also varied?
You should go to Rafaela's talk tomorrow and ask her that.
I'll ask her then. Thank you.
Okay, we still have time for questions if there are.
So you showed a plot earlier with like a linear relationship between the number of spectra of galaxies you're going to get as a function of time. So I was wondering, like, for prospects for the future, do you expect this trend to continue? Is it realistic? You say we're going to get like billions of galaxies in the not so distant future?
We don't have the money yet at the moment, but
assuming the money is around.
Of course, I mean, if we get the money, we can. And there are proposals such as MegaMapper or Spectel, or also in space, such as Cirmos, for example, that would allow a continuation of this. Yeah, usually with a bit of a focus, pushing towards redshift above 2 and filling out that parameter space. But I think yes, it is reasonable. Yeah.
Okay, any other question? What's that? What are the expected constraints on H0 from DESI using the turnover point? A percent level, 10%? Because you showed the results from not DESI, right? Not
yeah, no, this was EBOS.
Yes.
So it depends on what other information you add in, because you still have this degeneracy because with omega matter and H0. So you have this big banana, and this big banana will shrink, but it still will be a banana. Okay. We actually should do this with our newest forecast for year 1, but the last time, I think a few percent.
Okay. One question over there.
Maybe just ask you if you'd say anything about the primordial non-gaussianity measurement, the current value with DESI, and how well can you do better in the future? You know, how much better can we do in the future?
Yeah, so this is really DESI Photo C, right? So this is using the photometric survey that was used for the targeting, and then using the N of Zs from SV data. So it's not really DESI data. DESI. It's not DESI main. Well, systematics is a big problem. And even though we're trying our best to remove those systematics, very fundamentally, we're also limited by how good the maps of the systematics are, how good the extinction maps are, how good the dust maps are, because we cannot just pull a new map out of our hat. Another concern is, for example, also, how do you calibrate those systematic maps, right, as a 0 point for your photometry, because any offset in that will also shift your systematics around. And these are just the observational systematics. For that particular paper, I think after just 2 years of trying to figure out what's going on, you need to, pull a line and draw a line and publish. And we were very careful not to claim a detection of primordial non-gaussianity in this paper. But it is really, really hard. And on top of that, this is just the observation. Then you also have the theoretical problems. I think Alex Barrera is giving a talk. I'm probably going to mention that. How well do we even understand the connection between FNL parameter and U-scale dependent halo bias and so on? So it will be a challenge, and there's lots of work to do.
Okay, so thank you very much, Eva, for the nice talk and the nice answers. Yeah, and thank you both the speakers for this nice overview of 2 sides of the large scale structure. So we have some announcements. Tomorrow, the plenaries will be starting at 8:45. So check the schedule. We have lunch now. If you haven't uploaded your talk, do it soon, please, because people need to set up before. So we don't want to be like just behind the people. So make sure you send your talk already. And I think that's all right. Yeah, so let's go for lunch.
Thank you for sharing, for sharing. Do I need to, what do I need to do other than actually